I'm audible, right? Yeah. Okay, so good morning, everyone, again. So I already introduced myself. I'm Bidyut from University of Exeter, UK. And yeah, hope you all are having a good time. And so I'll be doing a brief introduction to atmospheric convection. It's so the idea that Vishal gave to all of us who will be speaking, and especially for the introductory courses, that we should build upon the talks that happened last time. And yeah, I hope some of you at least watched the talks. But it's so I just wanted to pop this word. Typically, when one would introduce atmospheric convection, then people would start with fascinating images of convection. So I thought I'll just do it a little bit in a different way, in line with what Professor Gopakumara said, that ICTS also is a place of bringing out your creative sides. So what I would request all of you to do is scan this QR code, and you will be taken to a page like this, and then you will type your name, and then you will use this free drawing pen, and then draw whatever comes to your mind when you say atmospheric convection. Okay, when everybody has taken a picture of the QR code, I'll just take it off because I need to go to the browser and see what you have drawn. So we were supposed to have an icebreaker, so consider this a mini icebreaker. Okay, I think this is... We already have some nice... So I can see some circulations going, deep clouds, tiny deep cloud, and hot and cold. And so I can also see some anvil already going. And there's some shorter and deeper. Oh, please do not edit, otherwise I'll have to keep editing myself. So some colorful clouds. So I see a plume written. So I don't know, sorry, I don't know how to make this panel smaller so that I can see all the... But I think this is more fun than looking at pictures. This is more fascinating images. And we'll already have... Okay, I think somebody drew convection in the ocean, Bay of Bengal. Oh, this is very colorful. Okay, great. This is Vishal. Okay, so we had some good images of cloud. I think I would say that attempt was successful. I had never used whiteboard before, and I thought it should not fail. Okay, anyways, so we all agree by looking at those clouds that I think we were imagining. Nobody basically drew a stack of cirrus cloud. When I asked you to draw atmospheric convection, somehow back of your mind, everybody had this idea of deep cloud, precipitating cloud. Nobody actually imagined a cloud that didn't precipitate, no matter how your sketch came out to be. But then I think every one of us was thinking of precipitation. And I think that sets the stage for our this workshop, because we essentially were thinking of clouds in the tropics, or at least the like clouds in monsoon climate, a monsoon environment. So before going to monsoon, I'll just try to define, okay, I think I was just doing the wrong thing by going forward with my keyboard. I can use this. Anyways, so let's define tropic first. and there are different ways to define, but I think I'm using this zonal mean, annual mean temperature cross-section with vertical levels so that we have, I promise you, I'm trying to give you an idea which you will find very useful towards when you will listening to talks of different speakers, because they will eventually, or most of them will try to use a concept of energy framework of convection. And this is basically my attempt to give you an idea of what that is. So basically, how we define tropics from this plot is the region where temperature is reasonably homogeneous. It doesn't vary. We see this, that over the extratropics or mid-latitude, the gradient of temperature is much stronger than what we see over tropics. And so I hope when I said zonal mean, annual mean temperature plot, it is clear to all of you. I'm not really sure what the distribution of our participants, but I'm guessing most of us are, like most of you are rather, like first or second year of PhD, and some of us are postdocs, maybe like us. So there is another field that I have drawn here, is zonal mean, annual mean, specific humidity. So just to give you an idea of the two major players who decide energy of an atmospheric column or atmospheric parcel, and both decrease with height. So when you look at the zonal mean, annual mean, specific heat profile, then you see it's very high at the tropics, core tropics, and it decreases fast. And the same thing we have already seen for a temperature, it decreases, but not as fast as specific humidity. So, yeah. So there are two forms of energy associated with these two fields. One is associated with moisture, which we know as latent energy. I have just given here some very basic, typical, or example calculations just to show you that we use this latent heat of vaporization to convert moisture into energy units. And also energy due to temperature of an air parcel, which we know as sensible energy. And again, we use this to convert our temperature to energy units. And what you notice here is the temperature form of energy or sensible heat is much bigger compared to latent energy. Nonetheless, it's not any of any lesser importance. So there is another form of energy which we will need to define or to understand the energy of an atmospheric parcel. That's the third player, and don't tell me it's Chris Gale. That's a trick question, and that's a misdirecting photo. So can somebody or some of you tell me what can be the third form of energy? Energy that increases with the height of the air parcel. Any guesses? Yep. Potential energy. So energy that increases with height. And again, in line with what I had drawn before, it's sensible heat, sensible energy, and sensible heat and latent energy. This is potential energy. We have all read in school. We had like H rho Z. That's how we remember. There is no rho here because rho is 1 for air. And yeah, GZ. And this value again, when you think of these three forms of energy, sensible heat and latent heat and potential energy, sensible heat is the largest of all. And then the sensible heat and potential energy and latent energy. When we combine all three of these, then we give it a specific name in terms of, in the field of atmospheric sciences, or at least when we will talk about convection, we will call them with a single energy name. Can you tell me what that name is? Monostatic energy, thank you. And we indicate it with the term H. And this, I think speakers later will thank me for introducing this quantity to you. Especially Michaela, I guess. So, and then I have just written for, just to code it with color, I have written latent energy in blue and other two energies in red, because we can group these two and call them dry static energy. And then comes the moisture part, which is latent energy. And these three forms of energy, or three terms, gives us monostatic energy, which we will see how it changes with vertical profile. What is its vertical profile? Because when we talk about atmospheric convection, all of you, what in your sketches you have noticed, we have this convection going up, clouds going up. And why clouds form or how they form, it's related to how the properties of our atmosphere or the atmospheric column changes with height, how the instability grows. So we wanted to see how monostatic energy changes. And for that, I had just plotted the vertical gradients of the zonal plots of specific humidity and temperature that I had drawn before. I just averaged or took the mean value between 20 south and 20 north. So I averaged the value between 20 north and 20 south and just plotted a gradient. And what we see is, like we saw in the zonal profiles, this is just more like a visual way of telling that moisture increases faster compared to temperature. Specifically, when you look at the bottom levels, it decreases pretty fast. And temperature kind of stays steady up to a certain level and starts decreasing thereafter. And I used NSET data, as I said, for this plot. And NSET data gives us at least moisture fields only up to 300 hectopascal. So yeah, I do not have the line above 300 hectopascal for moisture. And so did I keep the temperature up to that level as well. And so now I have plotted all three components, the sensible, the potential energy, and latent energy on your right-hand side panel. And then I have summed them to plot the monostatic energy on the left-hand side. And it gives a nice C shape because all three, if you see, moisture is decreasing and temperature is kind of steady and then increasing. And this one, moisture and temperature decreasing, and then your potential energy increasing with height. And when you sum all the three, then you get this curve, which is monostatic energy. And the reason I mentioned that I have data up to 300 hectopascal is, if I had plotted this up to slightly further up, then you would have seen the monostatic energy at the high levels is actually slightly bigger than what we have at the lower levels or near the surface. And this curve actually gives you many things to think about. It has a nice minima at the middle level, which actually encouraged many people to come up with schemes to model convection, looking at fixing different processes nudged to this level. For example, in some of the schemes, you see, I shouldn't coin the term downdraft yet, but because we have the earlier lectures with us, I can say, like, some people, for example, in a scheme called Grell scheme, they use this level for initiating downdraft. But anyways, so because we are interested in cloud or atmospheric convection, so what I would like to explore is how does this moist static energy profile look like for cloudy and clear sky, because that would tell us the difference between how the instability or how the atmosphere looks like between when we are having a cloud and when we are not. Essentially, it will tell us the region or what monsoon would look like in terms of moist static energy and what non-monsoon regions or clear sky regions would look like. So this, I have this tendency to go back and so for this, I did a slight trick. So instead of looking at specifically picking cloudy points and not non-cloudy points, what I did is I took 500 hectopascal vertical height. Does it make any sense to you? So it's the vertical velocity, sorry, not vertical height. So vertical velocity, we can take it as a proxy for clouds. So I took vertical velocity at 500 hectopascal, and I sorted it from lowest to highest value. And because I took pressure vertical values, so the negative values basically correspond to the regions where we have cloud. So the most negative values are the deepest of deep clouds. And the most positive values are subsidence regions. These are clear sky. So if I now plot MSE profile for the same grids where I have the negative vertical velocity, I can say that's my MSE profile or moist static energy profile for cloudy region. And when I compare it with here, moist static energy plotted for this part of omega or vertical velocity, then I have MSE for clear sky. So just to give you an idea of how my vertical velocity or vertical profile velocity profile looks like if I sort it according to my omega 500. So now you can see these blue patches are basically, and this is the bluest, which is my strongest updraft, and this most red part is my subsidence. And so yeah, I have just shown it with arrows, and now I'm going to plot moist static energy for these vertical velocities or strongest updrafts and strongest subsidence. And this is how they would look. Your ascending is, I have taken 0 to 10 percentile of the plot that I had shown in the last slide. And this blue one indicates the MSE profile for that region. And the red one is my downdraft. And what can you tell me any observations about these two profiles? What do you see? We of course see my ascending profile has a higher moist static energy. And I've said 1 because I wanted you to say 1 more if you see any more feature of this plot. Anything? Okay, it's easy. They have bigger difference at the surface than higher levels. Okay? So this is one important feature of this plot, which I'll come back to again at a later stage. So in this plot, I have taken the ascending percentile to be 0 to 10. If I just put it to 0 to 5, then the difference is even more, which is expected. I just wanted to show it to you that my deepest cloud will be even more moist. Natural to expect that, but this moist static energy framework gives us a nice tool to analyze our cloud. It gives a nice energetic framework to it. So, and if I take this blue profile, so I have just removed, I have taken this blue profile and put a cloud in it. That moist static energy profile is in the cloud, and I have, due to natural mass conservation, I have put this circulation associated with the cloud. Now this is what we want to explain, like what this means. This circulation, what does to the MSE profile within the cloud, or maybe I'm not putting it right. Like from energy point of view, what this circulation is doing. I have higher energy, higher moist static energy in this profile and lower moist static energy at the surface, the cloud going deep, and then this is the circulation going up in the cloud and then diverging aloft and then coming down at far away distance, and this is, there is low level convergence. Can any of you guess what this circulation will be doing in terms of when you look at this moist static energy profile of the cloud? Any guesses? It will export high MSE and bring low MSE. So this basically will be a key, or this concept we will use to look at monsoons under this energetic framework. That is, it exports high moist static energy from convective regions and brings in low moist static energy. So deep convection, as I said in my introduction to atmospheric, my version of introduction to atmospheric convection, I'll try to give you an energetic perspective. This is essentially what I was saying, that when we think of atmospheric convection, we typically, I mean, that is also fundamental. We typically think of all the instabilities, like all the theta V's and all the potential temperature or virtual potential temperature or T-phi diagram, CAPE, and seen those thermodynamic variables. And Maxime, Colin, who will be arriving next week, he did a nice job of introducing the last batch of participants with all those thermodynamic concepts. And when I watched his talk, and then I thought, if I do the same, then it would be just a repetition. And that gave me the motivation for doing, taking this approach of introducing atmospheric convection to you. So yeah, bottom line is a deep convection transports energy away. And now a very beautiful plot from NASA. This is precipitation climatology. I am doing a big jump. You will realize it's not a very big jump when I will explain the link between my previous plot and this one, that what we are looking at is about 23 years precipitation climatology, annual mean, and we can see all the deep convection within the band that we defined in our very first or very second slide as tropics. So the majority of convection that we see is in the tropics, and what we know from the energy point of view of global circulation, the tropics has this excess of energy, and in the polar regions there is a deficit of energy. I wouldn't go to the detail of that. I hope it makes sense when I say tropic has a surplus and polar regions has deficit. And this precipitation band, or ITCZ, Inter-Tropical Convergence Zone. I think Divya will talk more about ITCZ. And so this is so nicely related to this energetic framework that the convection that we see is a requirement from the energy point of view, that these deep convection that we see, it transports the surplus, part of it at least, is transported by this deep convection. And that having deep convection here is a demand from the energy balance point of view, not just thermodynamics. So I plotted this in a slightly more fancier way of plotting only the higher intensity rainfall, meaning I have just plotted the contours which indicated 10 millimeter per day climatological rainfall, and I have colored them from January to December. So each color of these contours, actually there is no point spending this much time explaining the contours because that's not going to help you anyways with the further slide or further plots. It was just my way of playing with the data. I just wanted to see how the precipitation moves from December or January to December. So like the reddish contours will be at the south of the hemisphere when the sun is towards in the southern hemisphere. And as you go progress in the year, then these greenish, yellowish, and cyan colors, we can see them over India because that's when the monsoon starts happening and we see the contours here. But main point I wanted to make is the ITCZ that we had seen before in the earlier slide. These contours actually indicate that this ITCZ rainfall is not just very weak type of rainfall. They happen because of strong rainfall. You have the strongest rainfall bands there. And to prove that, I have this MCS precipitation fraction. So this is again a measured observed plot from convective system tracking. And we have this annual mean precipitation coming from mesoscale convective system. So this precipitation that comes from mesoscale convective systems, they explain major part of the rainfall that we get in the tropics. And now I do not know if you know what mesoscale convective system is, or how many of you at least. So to check whether you know or how much you know, or whether we are thinking about the same thing when I say MCS or mesoscale convective system, what's the best way to check it? Just draw it. So again, scan it and draw it, and then let's see. Otherwise, I'll be speaking, and then it feels like I'm not sure whether you are, I'm making any sense or not. So then I know if I have to explain MCS or not. Yeah. Yes, sure. I'm just keeping it here because people are scanning, I guess. Yeah. Yes.
And we saw that the significant convergence of convection which starts, which is figured beyond boundary layer, above the boundary layer, elevated convection.
Yeah, I think it's. Yeah, I took the annual mean climatological omega. So if I had taken a high frequency omega or maybe more satellite. Yeah, you see, yeah. You see, but if I had taken more like high frequency omega and more satellite, I mean, more, it's omega from NSEP, which is okay, but still. So I think some of the things are missing. Even I had some missing data points there. So yeah, I mean, that's the latest plot I'm doing for even for my other analysis. So I thought I'll use it, but it's a nice nice way to visualize, but yeah, some things we need to understand better, I think. We can discuss, of course. Okay, so I guess we are again ready with some interesting plots. Okay. So this is a cluster of cloud, I guess. There is a Planck. Oh, there is some different cloud types. Okay, so I'll just, yeah, different cloud types. And we have 100 to 800 kilometers scale, 100 kilometers scale, more than 100 kilometers, so mesoscale. So people, I think I'm not putting a jargon which is totally unfamiliar in the room or among the participants. We have, if I do an AI recognition, then it would find like match between different plots actually, or different sketches, sorry. So when I said MCS, people essentially have drawn more than one cloud, which is interesting. Okay, someone is drawing, so I'm not gonna spoil the sketch. Great. Oh, yes. There's some tilt. Okay, nice. Let's go back to, thank you for participating in this survey. It helps. Maybe we can leave this with ICTS, that how people imagine cloud. So it's not just us, people before us did the same. I think it's not, these schematics are not very different from what we have drawn. Many of them in spirit. We maybe all of, I mean, we are not great artists, but in spirit, the sketches we did were similar to these ones. So I have taken this from Brian Mapes' paper, who looked at the mesoscale convection life cycle building blocks at different scales. And these sketches are from the works, earlier works. For example, this one is a mesoscale convective system looking at a square line. So this is from Gilles, slightly older paper, 1969. And this is, this is a square line. Again, what I'm going to show, trying to tell is all these different sketches are for different time scales or time and spatial scales. But the overall structure or building blocks, they look the same. So this one is a mesoscale convective system from GATE, which is one of the most, I find one of the most decorated field campaigns. And this one for, so now from a square line, now we have come to a 2-day wave from Takayabu 1996. This is again from a very well-known field experiment observation campaign, Toga Core. We have this. So now you have already seen these kind of sketches in your own drawings. And this one is for convectively coupled Kelvin waves. I'm just throwing names and not explaining them because I think there are people who will be able to, or who will definitely explain these things to you in lectures. I think, yeah, Eric has a lecture today. And then this is a Madden-Julian oscillation. from Lean and Johnson, 1996. So the essential or the basic point behind all these plots is they have this different cloud types or different structures, which is summarized by Brian Mapes and others with a very similar looking sketch that you just, all of you just did. There is a small shallow or congested cloud, and there is a deep cloud, and there is a trailing stratiform cloud. And this, they call it stretched building blocks. Stretched means there was a more condensed form of it, and filtered view. It comes out to be these three primary cloud types that typically we dominantly observed in the tropics when we said tropical rainfall is dominated by mesoscale convective systems. Then those systems essentially are like a group of, or is formed by these three types of clouds. And this is not just imagining things. So these three cloud types, because we know that clouds, through latent heating, it produces heating. So these three cloud types, we can associate them. I just color-coded, didn't want to draw lines pointing from here to here. So I just color-coded them, the deep one with a red dot. So the deep cloud would essentially produce a heating profile in the atmosphere, which will look like this, a big first baroclinic mode. And then the stratiform one, because the cloud is at the higher level, we have the heating at the higher level, and there is relative cooling at the lower level. And then we have a congested cloud, which is at the heating at the lower level. And these are just idealized profile corresponding to these three cloud types. But this is a plot from Shoemaker et al. To 2007, who looked at heating structures of TRIM data, which is a satellite observed data. And you can actually see the different heating types. So this one, by the way, just, so what Shoemaker and others, they did is they separated the rainfall in different intensities, and they had their way of defining that the higher intensity rainfall essentially come from deep rainfall, and lower intensity ones are stratiform rainfall. And the lowest intensity is typically clear sky, and so which has this upper level cooling thing, which is related to radiative cooling and all. But the major thing I wanted to convey from this plot was you actually see this, these three heating profiles in the atmosphere, from which is an indication that these three cloud types are dominant in the tropical, in the tropics. And people like Bolem Kuiter and Andrew Maida, who I just mentioned, I had mentioned in my introduction, they actually design convection schemes inspired by these three cloud types. And I will not go in detail of these parameterization schemes and all. I just wanted to mention that these observational aspects of clouds have motivated people to directly use this information to design convection parameterization schemes. But yeah, I'm just trying to think, how do I go to the next part of my talk? Because I'm going to change gear. And because I'm going to change gear, I'm going to start it with a poem from, so it's written by ChatGPT, but it's pretty good for what I wanted to say. So I'll just read the poem out loud. So it is, so I just wanted to write, wanted ChatGPT to write a poem in the same line as who am I? So when I end the poem, just tell me who am I? So I hug the earth, yet I am air. You rarely see me, but I'm always there. By day I rise, restless and tall. By night I shrink, subdued and small. I carry heat from surface to sky. So only modification I did, ChatGPT did land to sky. I just modified it to surface to sky. In invisible plumes, they twist and fly. Clouds above may steal the show, but I decide how high they grow. So who am I? Boundary layer. Great. I mean, this was easy, I guess. Much easier. Very easy. So I'll just go back one slide. Oh, 2 slides. And I think nobody noticed, or very few of you might have noticed, top of the boundary layer. I just wanted to point this after reading the poem loud, that clouds above may steal the show, but I decide how high they grow. So I'll just try to spend a few more minutes. Yeah, I have little time. I'll spend some time on boundary layer, and I promise I'll come back to the profile that of moist-static energy that I showed below, just to connect or convince you that my part 2 is not very different from part 1. So I'll just mention few observational facts, that there were some measurements, and we won't go to the detail, but just the boundary layer height over a surface is decides what would be the width of the plume that will be going up. And then also there was one observation that said from Lucas et al. 1994 that continental boundary layers they are deeper, and hence they generate wider updraft. So what essentially I'm trying to say is, over ocean we have a narrower and weaker updraft, and over land we have a wider and stronger updraft. So if I show you this plot from Matsui et al. 2006, who looked at different cloud types over different geographical locations from TRIM data. I think it was 20-year TRIM data. And they plotted, they had, from the satellite observation, they had separated the precipitation to deep and stratiform and different types. And what you can see is deep convection appears mostly over land. And for this, what they suggested is kind of a decision tree, or explanation tree rather. And I have highlighted this deep planetary boundary layer and stronger updraft and stronger deep convection. You can read through all the different terms in more detail, and there is some microphysics as well. But yeah, and they mentioned that over ocean it's just the opposite. But it might not be that simple, but still we can accept that for now. So continent has deeper boundary layer, and it has stronger updraft, which leads to stronger deep convection, as we had seen in this image or in this plot from Matsui et al. So for Indian region also, there are some recent MCS data. I mean, the data was global, but this plot is only for Indian region. Looking at, we remember somebody drew Bay of Bengal in convection sketch. So this plot, what it shows is it calculates or estimates lifetime of mesoscale convective system, and it also estimates the rain rate from those systems. And what we see, and of course the contours are for land, the red contours, and this blue shading is for systems over Bay of Bengal. And like what we saw, stronger and deeper convection over land and weaker and narrower convection over ocean. Consistent with it, what this plot shows is we have longer duration MCSs over ocean. And because it is longer, they precipitate more. Eventually, the rain rate comes out to be slightly more for ocean, but more, the more dominant message here is the lifetime of MCSs over ocean versus land. Over ocean, they last longer than over land. And so again, like a tree of, or I don't know what to call this tree, but anyways, it's an ocean and land contrast of how, what we had seen. So over ocean, we have a narrow and weaker updraft, longer lifetime. So what that means, the cloud would take more time to consume the instability in the atmosphere. And again, I'm throwing this jargon CAPE, convective abatable potential energy. I think you know what it means. It's just an indicator of instability in the atmosphere. And then in most of, not most, but some of the climate models or convection parameterization schemes, CAPE is used as measure of like how fast or slow it will be consumed. So, so over ocean, because it's more a longer lasting, we can say that it might take longer time to consume the instability in the atmosphere by the convection above it. And over land, it might take shorter time to consume the instability. So we actually did one test with this in a CAM model. I will share more results on my 15th May talk. Only thing I wanted to say here is by giving different consumption time scale for CAPE, we're essentially trying to mimic the effect of boundary layer on convection. And we did see some improvements. Again, those I will talk later in my talk. But those improvements, what it indicates is the importance of boundary layers representation in climate models, or in general understanding boundary layers role or handle in deciding how the atmospheric convection grows. So now we come back to this plot that I promised I'll show again. And if you remember, I had asked about a feature that we see in this plot, that there are very little or reasonably less difference in monostatic energy in the upper level compared to, I've just drawn this arrow 5 times just to show that it is much larger, the difference is much larger at the surface level than at the upper level. And if you remember seeing the moisture and temperature distributions or zonal, annual mean, zonal mean cross sections, then you would remember at the upper levels, the moisture already has less value and it has less variability. Temperature also, by design, we define tropics is the region where temperature variability or temperature varies very little, something we know as weak temperature gradient. You might have heard the term. So at upper levels, as a consequence of less variability in moisture and less variability in temperature, we see less difference in monostatic energy. But what happens at the lower level is there is more difference between monostatic energy profiles between clear and cloudy sky, which brings the boundary level or boundary layer processes or surface level monostatic energy is an important indicator. So one thing we need to keep in mind, though, that monostatic energy and clear and cloudy sky, or other precipitation and monostatic energy connection, it doesn't give us causality very clearly. We cannot tell which caused what, but we can of course get better insights about precipitation and atmospheric convection looking at more static energy framework or more static energy. And there is a nice paper by et al. 2010 on like convective quasi-equilibrium view of monsoon. So the introduction part of this paper is very nice actually. So almost whatever I said, you can get a good idea of that. And they have written it very nicely, that why the surface more static energy, we can relate it very well with precipitation or look at monsoon. So with this, I think I would conclude by two basic summaries of what we learned. We looked at deep convection with the lens of more static energy. So, and we saw that the cloudy skies has stronger more static energy than clear sky, and clouds act to transport energy away from it. And we also discussed land-ocean contrast of deep convection and emphasized how important the role of boundary layer is. So with that, I will conclude. Thank you. Yeah, enough time for questions, and we also have an empty. Is it still empty? We have.
Yeah, at 10:30 we'll have tea, but we could stretch this and take tea
Yep.
a few minutes later. Yeah.
No, it's not working. Oh yeah, it is.
Yeah. Hi, that was great. My query is about the slide number 19, I guess, where you show the magnitudes of vertical velocity.
Yep.
Yeah, so here in clear skies, you show downward velocities of omega almost same as the upward velocities. But we've been like through the literature or through the observations, we have seen like the descending motion is usually distributed over large area. The magnitudes are so small, but the cloudy areas are fractionally small in area, but intense vertical velocity. So is this normalized values or it's just the absolute values?
No, it is not normalized. That's a nice spot actually. I mean, spot in the sense, nice detailed look at the plot. So this is basically a climatological mean. I think it's related to what Vishal was asking. It's the climatological view of the vertical velocity. And it's many years data average for annual mean. So the signal that you were looking at, we have strong updraft. If I plot it for, and it is also for monthly data, if I remember correctly. So if I plot it for very high frequency data, at least daily data, and yeah, do not do that much of an average, then you would see it more clearly that we have stronger updraft. And then your red patch will also stretch. The blue one will be much, blue patch will occupy much lesser space.
Yeah, and the last flow chart where you distinguish between the Cape concepts over ocean. Yeah, here. So I think Simona during the last workshop or a few workshops earlier as well, she used to show that over the ocean, the Cape or the rate of change of Cape is almost equal to 0 or approximately equal to 0. So what is your opinion? She says that over the land, the Cape gets time to build and then convection is realized and Cape is utilized. But over the ocean, it isn't that way, and the Cape isn't allowed to build for a longer time scale. So that is what I've been hearing through past ICTP lectures or ICTS lectures. So what
Is allowed to, you said, or is not allowed to?
Yeah, especially think over the ocean, the cape isn't allowed
Means
to accumulate
oh, it's
compared to
immediately realized, you mean?
immediately realized in the form of convection.
Yeah, it's a different take, I guess. So even like there are some papers, I forgot exactly, that find cape to take longer to consume over ocean, but it's not, I think it depends on, again, the frequency of data that we're looking at, and case to case, it might change. It is a very, and cape also is, I think, how you define it, but it is not really contradictory, but it's looking at things probably in a slightly different manner. But yeah, it is. Yeah, I think we can discuss about this, looking at, because when I was doing this, there was another study I found which looked at cape varying dynamically at every place. So it is not very, it's a very crude separation of surface, just having land and ocean. But depending on where you are looking at in the ocean or in the land, you might find different results, especially if you look at the actual results and not theories.
Okay, thank you.
Yeah, thanks for the talk. I had a question about the precipitation contours that you showed. Precipitation contour. Yeah.
Yep.
So here we can see that for the western side, we see precipitation more accumulated towards the western side, whereas for the eastern sides, that is India and the countries on that side, we see precipitation more accumulated on the eastern side. Is there a specific reason for that?
Is there a specific reason for that? I don't know. Is there a specific reason any of us can think of? Oh. He doesn't have the mic. So why there is more precipitation on the eastern side?
Normally, the precipitation combines convective precipitation and large-scale precipitation. So your slide shows this is GPCP daily precipitation, total precipitation. Whenever you distinguish two precipitations, the large-scale precipitation will be different than convective precipitation pattern. So normally the large-scale precipitations dominate sometime in monsoon season than convective precipitation. So recent decades, the convective precipitations are higher than large-scale precipitations. So the moment we can see the precipitation in monsoon season normally transfer from the ocean towards the land. So the pattern is look better when you distinguish two precipitations and see the pattern of how it changes. So if you plot two precipitations, convective and large scale, so you can see the clarity how the precipitation band shifts. So
yeah, thanks for the comment. But this plot was not partitioned into convective and a stratiform. And even if I look at TRIM data for annual mean, then you would still see more precipitation on the eastern side of Indian Ocean, for example, like the region where what you specified. And that's, I think, part of the fact that the monsoon, at least the rainfall that we see here over like Myanmar coast and all, so because the monsoon circulation goes from west to like southwesterly flows. They go and it precipitates a lot over Bay of Bengal because Bay of Bengal is very, very hot during that season, and like monsoon precipitation naturally dominates the whole annual rainfall. So here it is plotted annual rainfall, but even if I plot just for monsoon season, then you would see sort of similar picture. And why I think there's a paper by Bill Boos. I do not remember the details of it, but then he plotted the precipitation along tropics, I think over like 5 south, 5 north averaged, and also plotted the topography of it. So you find all the mountains, and then just before the mountains, there is rainfall. So it's part of the geography. Like if there was no mountain, probably you wouldn't have seen these rainfall maximas there.
Yeah, I'll add my 2 cents. I think you had 10 millimeter per day contour.
Oh yeah, next one is, yeah, I just wanted to show where the heavier.
Probably I think maybe Arabian Sea is colder as compared to the Bay of Bengal and West Pacific, closer to the deserts. Also, I think the eastern part of the United States will also have a lot of precipitation, but on synoptic scales, I guess through these cyclones, which I think you filtered because you did this.
Yeah,
I mean, that's my
kind
of 2 cents, but maybe others have their things to add.
May I? May I? Could you just go to the previous slide? It's something which I notice. I don't know how relevant it I may be wrong, but I do observe that the precipitation here follows the ocean currents as well. If you look east of Asia, we can see a high precipitation where Oyashio current exists, and east of the US where Gulf Stream exists. And the Peruvian current west of South America, it's a cold current. So it seems like the precipitation is following that as well.
Yes.
Storm tracks.
So, sort of, yeah.
Also, like just by going at what ocean currents you mentioned, Kuroshio current and Gulf Stream. So they are warm waters. So typically precipitation would respond like more efficiently to warm sea surface temperatures.
The eastern part of the Indian Ocean, especially during monsoon season, is quite cold because of the upwelling along the coast of Africa. And so that suppresses precipitation there. And then, yes, of course, you do get this enhancement in the presence of orography. So here, well, you cut through the Western Ghats, but you can squint and see there's a little maximum precipitation there, and then the Myanmar mountains. So you do see those orographic features. As for the currents in the, I think Vishal made the right point that the main thing we see here is those are storm tracks, but it's also true that you can see the features of the warm water in precipitation. In fact, we made at a certain point a 5-kilometer resolution climatology of rainfall from the TRIM radar. And you can actually see these incredibly fine features of where rainfall really gets enhanced over warm water. So you actually see the difference between the coastline and just off the coastline where the water gets warmer. So it's a combination of the synoptic scale and these fine features of where the warmer SST is.
There was one more question, I think, here.
Thank you so much for the talk. I had one small doubt regarding the comparison between ocean and land regarding updrafts. So maybe you mentioned, I don't know if I missed it or not. I'm not able to connect the point where, here in this flowchart, like ocean.
Hello? Yes.
Okay. So ocean has narrower and weaker updrafts. And also it takes more time to consume the cape. So the system is going to be a little longer, I'm assuming. I'm not able to connect the narrow and weaker updrafts to a longer lasting system, and also contrary for the land, if you could.
Yeah, that's a good point. That's not very straightforward, and maybe it's not as straightforward as I have mentioned here. And it doesn't necessarily need to be, not necessarily true, I guess, in some sense, that weaker doesn't necessarily have to be narrower, but it's just an observational information that we have, that it has a narrower and weaker. So when I was doing this, I was more focusing on the duration, and I used this logic just as a background. And because I was more interested in the length of how much time it takes to consume cape, I wasn't really paying attention, or like not that concerned with whether the plume is narrow or wider. So yeah.
Water vapor is quite precious over land, so convection really has to work against drying and moisten systematically so that convection builds up. I guess that's what you mean, right? That convection has to build up till the other competing convection, and then some cumulonimbus might, whereas over ocean, maybe availability of water vapor is not limit. So you could have weaker updrafts, all of them surviving, not necessarily competing for water vapor. That's how I was.
Yeah.
But I guess this is probably a loaded question. I'm not sure.
Yeah,
the
yeah,
answer is known, but if others have any thoughts.
Because this was, I just did, I mean.
Is this from that paper that you showed?
Yeah, it's from
before?
the paper, and I'm saying I did, or like we did, but it will make more sense when I'll show the results. But even though, even if I show the results, the logic behind it, why I use the longer cape, longer time scale over ocean and shorter over land, is like the logic is still pretty debatable. I mean, so yeah, because we can continue to discuss that this parameter tau, the time scale to consume instability in the atmosphere, is pretty relaxed. I mean, it's a chill guy. You can give it any value and model doesn't crash. It continues to run. So people like Vishal, I think you did tau with infinite value,
Yes,
right?
yeah.
Yes. So Vishal did the extreme, and he assigned infinite value to tau, and model still runs and gives you some meaningful results. And what people had earlier noticed, that if you make tau longer, then the model somehow gives you better results. Probably it somehow supports memory of convection if it lasts longer, but it's not, again, very straightforward. But my idea was, what if we give two different tau values to ocean and land, just to represent land and ocean differently in a climate model? So yeah, so tau is a lucrative variable from a climate model context. So people have also checked different variables in climate model, like how sensitive a climate model is to different tunable parameters that we have inside a model. And tau is one of the variables that a model is very sensitive to, at least for community atmosphere model. And so, yeah, people have tried like 1 hour, 2 hour, 3 hour, 4 hour, 8 hour, and Vishal was extreme infinite time. And so I used just 1 hour for cape to consume over land and 4 hours over ocean. And I did different sensitivity studies, like having same value, longer value, but same over both ocean and land. And as you would see in my talk, that I have better results when I have a longer tau over ocean and shorter over land. But for today's presentation, only thing I wanted to convey is there is this different surface boundary conditions that that is important for how convection behaves in the free troposphere.
Hello, sir. Hello, sir.
Yeah.
In one of your slide, you have shown that MSE is decreasing with height
The MSE is decreasing with height.
within the cloud. Yeah. So if there's a cloud formation going on, so there is a convection. So we are in a convective regime. So how can MSE is decreasing? It should be constant, right? Within a cloud.
Within a cloud, what do you mean?
If there is a cloud formation happening, so the profile should be a pseudo-adiabatic profile in that case, the PT profile. So in that case, MSE should be constant within a cloud.
So cloud will still be buoyant, but colder than surface because your surroundings is colder than surface when you are going up. And if you're colder from an absolute point of view, you have smaller sensible heat, and overall energy of the cloud will be less at this point. It will be less than this point. So your MSE profile will look like, I mean, MSE value will be smaller than surface in the cloud itself, but compared to the surroundings, it will be more, of course.
So MSE, what the extra energy that is reduced, where it go this energy? MSE that suppose we are considering a adiabatic air parcel model, that considering the energy will be constant within the parcel. So if the parcel is moving up, and energy should be conserved. If it is not, then where this extra energy goes?
Okay, I'm not sure I understood it correctly.
Saying that as the cloud develops
Uh-huh.
at cloud scale, moist static energy, which is already accounting for latent energy, shouldn't that be conserved, considering it shouldn't care if precipitation is happening or not, should just be conserved as you rise up, unless there is some dry air mixing, which you are not considering. But I guess in this case, you are saying larger scale, not just cloud scale moist static energy, I believe. It would be neutral, constant with height. But this is the large scale profile maintained both by all the processes.
Yes.
Convection, radiation, and dynamics. And the flows are just carrying converging or diverging moist static energy. So his question is, if I were to plot moist static energy, does it really look like this minima and growing with height within cloud? That's his question.
Within cloud.
I guess it in Holton, in tropical dynamics chapter, there is actual Sonde observations from cloud. So it shows you tropic wide average, which looks like this. And if you were to average over a cloud cluster, then it's neutral. That's the job of convection. Keep making it neutral. Radiation and dynamics will keep on making it unstable. And when the flows act on this, I guess that's the energetic argument.
Yeah.
It's worth checking both.
Yeah, I think
neutral and
that's a good point, I guess.
Is there any other question? Amongst online speakers, if there is any question, I request ask one by one. We will wait for a couple of minutes.
So do we have any online participants?
There are some people online as well on Zoom. Let's wait for a couple of minutes or so. Well, okay, if not, then let's thank Bidyut once again for the nice lecture building on top of Maxime's introduction for convection. Yeah, thanks.